Good evening. Today we're going to start chapter 8 in the book. It's about HCS12 Timer Functions. These are the main topics that are covered in the chapter, the free running counter, and they call it Tcnt, the Tcnt timer or counter. I'm going to talk about it, how useful it is, how we can use it. We're going to talk about something called input capture, output compare. Some of you may be familiar with these, some are not. Pulse Accumulator and PWM. PWM here is going to be two parts, one about the 8-bit PWM and another one about 16-bit PWM. I think we'll take like 3 to 4 lecture meetings to cover the content. Why are timer functions important? I'm talking about timer functions that are based on hardware background. Did I forget? Yeah, that are supported by hardware. If you remember, in the interrupt chapter, we covered an interrupt called real-time interrupt, and we were able to generate periodic interrupts that we were able to use to generate something every amount of time, use them as a background for a delay, hardware-based delay, or periodically call a function or a task or whatever. Well, this could be probably not enough. We may need more of these things, especially in real-time systems. So usually in every microcontroller, there are things called timers. Okay, and timers here, by timers we mean special registers. Okay, special registers that you can control through hardware. You can control how fast they can count. Okay, so if any of you studied in their undergrad the PIC microcontrollers or any other microcontrollers, timer 0, timer 1, if you remember those, we have things like that here. We have a timer called the Tcnt timer. It is a 16-bit register. A 16-bit register, okay, with a clock source that we can control its frequency. To make this timer 16-bit count from 0x0000 to 0xFFFF, yani from 0 to 65,535, right, before flipping over again. And if you can control the clock frequency here, then you can control how fast this is going to count, and then control how fast it's going to overflow. And overflow or flip over could be programmed to cause an interrupt. So you can use it to generate interrupts. We're going to talk about applications, but to make the picture clear, we're talking about registers supported by hardware, counters. We call them, sometimes we call them counters or timers. They're sometimes interchangeable, the terminology, but they're the same thing, registers that count. But if we know how fast they count, and where was the starting point, the end point of counting, you can use them to time. Right? You counted 1,000 times. Every count you were at 1 megahertz increment frequency. Then you had 1,000 microseconds, right? So 1 second, and so on. So counters, timer functions are very important for time delay generation, measuring time between events, measuring periods, pulse widths, generating frequencies or measuring frequencies, counting events or generating events based on time, computing arrival time, track daytime, generate periodic interrupt just like the real-time interrupt, generate waveforms, and so on. All these things read support from the hardware through timers. The HCS12 microcontroller has a timer module called TIM, timer module. This timer module has 8 channels of input capture, output compare. I'm going to talk about this. What does it mean? It has a pulse accumulator to count pulses, 16-bit pulse accumulator, 16-bit timer counter, free running counter, and an enhanced timer module, and an enhanced TIM, they call it an ECT, that our HCS12 we're using in this class is among those who has an ECT. In addition to these, it has also 16-bit buffers for the input capture channels. It has, in addition to the 16-bit pulse accumulator, 4 8-pulse accumulators. It has a 16-bit modulus countdown counter with a scaler that you can control the speed. 4 user scale selectable delay counters to increase input noise immunity, and the 8 channels here we mentioned, the 8 multiplex channels that you can use the input and output compare functionalities are shared with port T 8-bit. Okay, so you can use them as a parallel port T, or use them as input capture pins or output compare pins. What are input capture pins? What are output compare pins? We're going to learn about them. But HCS12 or its the controllers that came after it from the same family are really one of its main characteristics or features that made it very popular in many industries, and among those is the automotive industry, is its power in timing. You know, when you control an engine controller, timing is really critical, right? For when to spark, when open a valve in the combustion engine, when to exhaust, and all these things, very precise timing. So this is a general block diagram of the timer HCS12 timer module. First, everything here is based on the bus clock. So the bus clock could be directly coming from it is the core clock divided by 2. It can come from the oscillator directly or the oscillator through PLL, right? Divided by 2. Okay, this bus clock, this clock can be pre-scaled. You can slow it down to trigger a timer here, a 16-bit timer or counter. We call it the Tcnt, the T counter. This counter would work in the background, and the beauty of it, it will be counting while your code in the main loop doing maybe something else, doing nothing or whatever. It will be counting the background in the speed provided to it by the clock we get from the eBus after the prescaler. Okay, so you will know the speed, the frequency. So you will know how fast this is moving. Okay, and when it reaches its maximum is 65,536 35, then another clock would flip it over. We can configure a timer overflow interrupt to occur on the flip over. Okay.
دكتور بالنسبه للتريجر هون بت باي بت بيعمل تريجر
The clock here, you mean?
Yes.
The clock, Mustafa, يعني a counter will, I don't know what you mean bit by bit, but it is, okay, what is this? It is, it is a register. We have a register called Tcnt. طيب. Tcnt, you configure its clock. It is a register 16-bit in memory. It has an address. Okay. Okay. And it has a clock source. Clock after going a prescaler to slow it down. Prescaler. Okay. So if you have 1 kilohertz here after the prescaler, this means this will increment every time, every t equals 1 over 1 kilohertz equals 1 millisecond. So every millisecond, this will increment. So you can read, ممكن انت in your code, Mustafa, you can say in your code, this is my C program, you can unsigned character أو مش character, integer لأنها 16 bit. أنت مثلا x, y. You can write your code to say, and you configure يعني enable the TCNT with its speed. وتيجي انت تقول له in your code x equals TCNT, and then do some stuff, then y equals TCNT. Okay. Then the count, the difference of count, difference count, y minus x. هذا راح يكون the number of counts it took to count يعني from here to here, صح? So assume in your count home when you read this register it was 0x00 I don't know 05, and when you read it here it was the reading was y 0x 0 I don't know 101. طيب. This means that the difference is the subtraction of 5 minus 1. خلينا نقول 1 هاي عشان تصير أسهل. فبتصير 0x0100 hexa counts. Okay. These are counts times 1 millisecond, and you get your time delay in milliseconds that it took it from here to here. So you can compute the time, the code, or the time you spent on executing this piece of code, مثلا. Assuming that it did not, the counting was not so fast and you didn't overflow. And if you overflow, we can compute this. But back to your question, every bit, every rising edge, يا مصطفى, the 1 kilohertz, هذه from a rising edge to a rising edge is 1 millisecond. So every 1 millisecond, this will increment plus. يعني it was 0, then it will become 1. يعني 0, 0, 0, 0, 0, 0, 1. Another 1 millisecond, it will become 0, 1, 0, 0, 0, 0. Then another 1 millisecond, 1, 1, 0, 0, 0. A 16-bit number keeps incrementing.
تمام. هلا ممكن decrement ولا بس increment؟ الفكرة إنه increment.
This one is increment. This one, the TCNT, is increment. ماشي. هلا we have a modulus countdown timer. هذا لحاله. That counts from يعني that counts down. This is not it. This counts up. هذه counts up. Okay. Okay, so this is the 16-bit Tcnt counter or timer. We have many control registers here to control the operation. We have a pulse accumulator. This is a counter that counts. يعني له clock. The clock is not the same clock of the bus. Okay, you can feed it a clock, a pulse coming from somewhere, and it will increment every time a pulse comes. So you can be able to count pulses. Every rising edge you increment by a 1. So you count pulses. This one also counted pulses, but the pulses of the clock. Here you are able to count other pulses other than the clock coming from other input pins. Okay, it is a 16-bit pulse accumulator, and we said the enhanced timer module has, in addition to this 16-bit pulse accumulator, it has 4 8-bit pulse accumulators. And we have 8 channels: channel 0, channel 1, up to channel 7 of input capture / output compare. A feature that can be shared or configured as input capture or output compare. What does input capture mean? What does output compare mean? Let me explain them quickly. I'll come to the details later on. But these features, input capture or output compare, they all they all share the pins called IOC0, IOC1, IOC2, up to IOC, and input, output, capture, compare 0, 1, 2, 3, up to 7. These are shared with port T 0, 1, 2, up to 7. Okay. All of these on an input capture event or output compare event, they all can generate interrupts. Okay. The pulse accumulator on an overflow can also generate an interrupt. The pulse accumulator on a pulse accumulator input on a clock coming in also can generate an interrupt. So see all these number of interrupts that we can generate. A lot of interrupts that are directly connected to physical pins that you can generate hardware signals if in case of output compare, read input signals in case of input capture, and have any of these events create or cause an interrupt service routine to go run, interrupt the CPU, the normal flow of the CPU. Okay, let me talk what is input capture, what output compare roughly, so عشان ما نكونش so that you are familiar with the terminology, and go back then to the details. So we have a Tcnt counter. Okay, counter. This is running in the background. Okay, always, and if you enable it, counting in a certain speed controlled by hardware, and counting in the background. An input capture has an input capture register, input capture register, data register, let's call it. Okay, and this Tcnt, المفروض they have the same size, 16-bit, and this one is also 16-bit. Your microcontroller, HCS12, has an input, a pin called IOC0 that can be configured as input capture or output compare. Let's talk about input capture first. And you saw the register, so the input capture register or output compare. but they both share the same pin. In the input capture mode, you want to capture the value of the timer on an occurrence of an event on the pin. يعني you go configure في configuration registers, you configure them to capture the free running counter, the Tcnt, on an incoming event. This incoming event could be a rising edge or falling edge, or both. يعني يا شباب, this is your controller. This is the input capture 0. And here you have whatever, يعني something that caused a falling edge or a rising edge. Let's start with the rising edge. ماشي. The rising edge, well, could be coming from a button you pressed. It could be coming from any sensor. The button could be on your door or window. Okay, whatever. Something that causes a rising edge. Whenever this rising edge comes, the hardware inside, you have a Tcnt counting up all the time in a speed that you know. And you have another register called the input capture register, the IOC, this one, the input capture register. Let's call it IC, input capture 0. When an event happens, you capture the timing. So an instant at the moment of this rising edge, if assume this counter was at 0x11f2, this will be take a copy to the input capture register 0. Let's see high 0x11f2. And the Tcnt will continue counting. So then another input capture, another rising edge مثلا بعدين happens. You did not change the configuration. هذا continues counting. Maybe its value became 0x2233. Okay. In the meantime, you can get interrupted or check a flag that the first rising edge came. You can go save this value somewhere and store it at somewhere called edge 1 in integer, unsigned integer. Then on another rising edge, this is going to keep running. It will be captured. You will be interrupted or notified through a flag or whatever. You can go take this value and store it at edge 2. Now you will be able to know the counter event at edge 1 and at edge 2. If you know how fast the Tcnt, you know how fast it's counting. You set its frequency. Okay, you will be able to know the difference, how many times it counted. Okay, and if it counted 1,000 times, and every count takes 1 millisecond, so this is 1,000 milliseconds. 1 second between the two rising edges. You can be able to configure the event to happen on a falling edge if you want. Yani after the first time you receive the rising edge, you get interrupted, you got the Tcnt value captured and saved in the input capture register. You can write code inside your interrupt service routine that next time, don't interrupt me on another rising edge, interrupt me on the falling edge. So you can go capture on the falling edge, and you will be able, in this case, to measure the pulse width. You can configure it to capture either on a rising edge, falling edge, and in this case, you will be able to know the timer value here, the timer value here, the timer value here. You can compute the period, you can compute the pulse width. Okay, so this is the meaning of input capture. Input capture means capturing the free running, the TCNT, free running counter, capturing its value at a certain point of time when an event happens on an external pin, and saving it an instant of that counter in an input capture register to use it for measuring time or whatever, to understand when an event happened or whatever. So this is the meaning of input capture, okay? So in input capture, we're talking about something is going to happen on an external pin, and you will need to, or you will be notified what time this thing happened and what was the value of the counter. So this is input IOC 0. So you can configure it as input capture. You can also configure it as output compare, but not at the same time, okay? In output compare, you also have the TCNT. See, the TCNT is the base for everything. The TCNT running. Okay, running in the speed you configured. It's a register counting 16-bit. Okay, has a clock. You configured it, and you were asked to generate on port T0, which is in this case IOC0. Okay, generate a 1 kilohertz square wave with 50% duty cycle. So you're asked to do this, to generate a square wave form forever, where this is 1 millisecond, any other 1 kilohertz, and this is 0.5 millisecond. Okay, so to be able to generate a waveform in a very precise timing without using any, go make port B equals 1, delay 0.5 millisecond, then go down, then without doing this, you want a special, very accurate timer function to do this for you. You can say, you can do comparison. Did the timer count? Let's assume you went and configured this counter to increment every 1 microsecond. You did this configuration. So you want to cause a rising edge. Then count 500 microseconds, count 500 times before going down. Then count another 500 times before going up. So you can say you have a register called the compare register, compare register 0. Okay. You know that this is moving, this is counting 1 microsecond, counting up every 1 microsecond. So after 500 milliseconds, the value in here plus 500, the value in here plus 500, yani TCNT value plus 500, you store it here. Yani مثلا at this value, port of time, this one was 100. or 1000, whatever. So 1000, when it becomes its value 1500, then you count it 500 times. It's time to cause a rising edge. So you go take the value of the TCNT counter, add 500 counts to it, store it in the compare register. Now there is a hardware that will keep comparing the value of this register with the value of this register. When they match, you pre-configure what to happen on the pin. You say, when these match, you go generate a rising edge. Then you get interrupted and notified. You say, okay, after another 500 milliseconds, I want to go do a falling edge. So you go and get another copy of TCNT, and 1501 مثلا, plus 500, 2001. You store it here. After 500 counts, the values are going to match and the falling edge will occur. Okay, and this will keep happening forever. So you output compare. That's why you call it output compare. You're outputting a signal on a pin, okay, on a hardware pin, when you compare the values of two registers, if they match or not. If they match, you produce a rising edge or a falling edge. Now, in your code as an embedded software engineer, you configure how fast this is going to count and what is the value that you want to compare with, and do an event when in case the match happens. Okay, this is the meaning of output compare. So usually we use output compare to generate square waveforms. We use input capture. To measure timing between events, between rising edges, falling edges, rising edges, and rising edges, whatever. Okay. So this is the concept of input capture and output compare, and both of them have a data register to be compared with, and have a reference, the TCNT free running counter. This one. Are we good so far?
Yes, Doctor.
Okay. You cannot, at any instant of time, configure a pin or a module or a channel as to work in the input capture or the output compare mode at the same time. It either has to be input capture or output compare, but not both. Okay. And we can get interrupts when a compare happens or a capture happens. We can configure interrupts. طيب. Let's go back to the TCNT and see how this is useful. Standalone, without the capture and compare, as a standalone free running counter. The TCNT is a 16-bit register, which means it counts from 0 to 0x f f f f, يعني 0 to 65,535. صح؟ يعني it counts, it overflows after 65,536 counts. It goes back to 0. So if you decided the clock rate that it increments, and you know, and so you know how fast it counts, you know how the range it counted, you can use it to compute timing. Example, if you have a bus clock of 1 megahertz and you pre-scaled this with 1, and you did not pre-scale it, 1, and you used the clock as is, this means you're getting an increment every microsecond. So time equals 1 over 1 megahertz equals 1 microsecond. An increment every microsecond. So a 16-bit register, and 1 microsecond, this, which is 2 to the 16, right? Times 2 to the 16 microseconds, you get 65 milliseconds before rollover. You can configure an interrupt to happen on a rollover or an overflow. So you will get, in this case, an interrupt every 65 milliseconds, a periodic interrupt. Okay. Now we know how to do periodic interrupts through the real-time interrupt, but this is another way. طيب, let's assume you want to generate, and I wrote an example in another slide. So an overflow here will happen every 65 milliseconds. طيب, لو بدي, if I want every 10 milliseconds to happen to have an overflow, what would I do?
بدي اعمل بري سكيل هون للفريكونسي.
افرض you're not allowed to do pre-scale. Yes, thank you, Mustafa. That's what you said is correct. Yes, you can do pre-scale. But what if I don't allow you to do pre-scale? I want you to think of something else. What else can we play with? You're not allowed to play with the pre-scale. You don't have the control of the clock. What else can we control? Where do we start counting from?
ممكن نعمل ماسك هون بحيث ابدا او
where
16 bits كاملين.
Yeah, so the Tcnt, Mustafa, it's a register we can write to it. It doesn't have to start from 0. You can write it, okay? So you can, if we want 10 millisecond before overflow, then how many times do we need to count? 10,000 counts, صح? 10,000 counts, صح? 10,000 counts. So I can write in the Tcnt timer, it's maximum 65,535 minus 10,000. صح? So before overflow, so write this to it, صح? So its value will be what? 55,000, صح? And you write in it 55,000. Correct? 55,535. So it will overflow after 10,000 counts. يعني 10,000 microseconds. يعني 10 millisecond. صح? When it overflows, it will go back to 0. صح? It will go back to 0. But you can cause an interrupt to happen at the overflow. Inside the interrupt service routine, the first thing you write in the interrupt service routine, the Tcnt, go write 55,535 in it again. So it will keep all the time counting from 55,535 to 65,535, then 0. Then you brought it back to here. So it will keep counting 10,000 times forever, causing an interrupt every 10,000 times. Right? So you get the... Yes, Mustafa?
Initial 55.
Yeah. You can write it. You can make it initially start counting from 55,000 بدل 0.
تمام.
Okay. But when it overflows after 10,000 times, it's going to become what? 0. So manually inside the interrupt service routine, you need to make sure to rewrite the 55,000 again in it. طيب. Anyways, so this is a very good and nice feature that you can use the Tcnt free running register alone to generate periodic interrupts. And the periodic interrupts, you can use it to increment software timers, counters, to enable tasks. You can use it to generate time delays, whatever, okay? As long as, we saw some applications when we did the real-time interrupt. As you're able to do an interrupt every amount of time you control, you can do many things, okay? طيب. It is also, the Tcnt register is also required, and it is a core for the input capture functionality and the output compare functionality. Okay, the value, the output compare compares with is the TCNT, and the value that is captured when an event happens on the input pin in the input capture is what is captured. The TCNT value is captured. Okay. But when you read the TCNT value register, you have to read the 16-bit register, the 16-bit at once. You cannot, if you're doing assembly, go read the lower 8-bit from a memory location, load it to A, then load the other 8-bit to B. You have to load D at once, okay? Load it at once, because it will be running in the background and you get an incorrect value. The registers related to it are 2 control registers and 1 flag register. And we'll look at them. So the timer system control register 1, we're gonna look at it in the figure. Let's look at it. And a few 2 bits here that are very important. This is the control register 1. To allow the timer to start time counting, you need to enable it. So this is the bit to enable it. Okay. If you write a 0 here, you disable the timer. It's not going to count. So this is a core control bit. These are what is going to happen in the wait and freeze mode. Let's ignore them for now. Yeah, you can keep the timer running in the wait mode or stop mode, or stop it. Up to us. But since we were not covering the freeze and stop mode, we don't care about them right now. And there is a bit here called fast flag clear. Fast flag clear, timer fast flag clear. Enable it or disable it from this bit. What does fast flag clear mean? 0, there's no fast flag clear. And you have to timer flags, you clear them in case of interrupts or whatever happens, you clear them manually. A fast flag clear, when the explanation is here, T flag 1, this a read from an input capture or a write compare channel causes the corresponding channel flag channel. What are the channels we're talking about? These channel 0, 1, 2, 3. Each one of them has an interrupt and a flag. Okay. So to clear the flag when an interrupt happens, or if you didn't even enable the interrupt, a flag will raise when the capture happens or the compare happens. Okay. After reading the value, you need to clear the flag to be able to be notified the next time. Okay. Reading or writing. Any reading from the input capture or write compare channel registers will clear the flags if this is 1. And you don't have to go clear the flag manually. It will be cleared automatically if you read the capture or compare registers. Okay. For T flag 2, any access to the Tcnt register clears the timer overflow flag. We said the Tcnt register, this one, will count when it gets to the maximum, it will overflow. We can enable an interrupt. Also, this will raise a flag. To clear the flag, we have to go clear it manually in the bit where it's saved. Or if this register bit is enabled, fast flag clear is enabled, just reading the Tcnt and saying X equals Tcnt, this will clear the flag automatically for us. Okay. For the pulse accumulators, same thing. So usually we enable this bit. So this register, the TS timer system control register 1, usually 0x 1001 0000 is written to it, so 0x 90. Okay. To enable the Tcnt counter. We just enabled, we did not configure the timing yet. To configure the timing and the interrupt, there is the timer system control register 2. Bit number 7, this one will enable the interrupt or disable the interrupt. enable. This is the local enable of the timer overflow. We call it TOF, timer overflow. Yani after counting, you're at 65,536. You got a click, you're back, you rolled down and you flipped over to 0. You can get an interrupt. Okay, to make this interrupt happen and interrupt the real flow of the program, you need to make this bit a 1. So we make this bit a 1. These are zeros by default. Now this bit, timer counter reset enable bit, I'll tell you what it does, but we don't need it now. If you enable the 0, will inhibit resets and keep the counter counting forever. طيب. If you make it a 1 here, if you make this a 1, then channel 7, timer channel 7 is compared with the Tcnt timer. Yani timer channel 7 is compared with the Tcnt are compared. If they match, reset Tcnt. Clear? So if you go write TC7, 0 in it, then, and this bit is enabled, 1, then what is the value of your Tcnt all the time? Tcnt is 0. And it matches TC7, it will reset. It will not count. It will go back to 0. 0. It tries to count, it resets. It tries to count. So the Tcnt will get stuck at 0 forever. طيب, if I write TC7 in TC7 FFFFF, you will count from 0 to FFFFF. Then you will go back to 0. You will reset. You will not overflow to 0. So you will not get an interrupt. The timer overflow interrupt will not happen. You will never roll over. You will never get an interrupt, even if the interrupt is enabled. Because every time you get to the maximum, you don't roll over, you reset. Is that clear?
Yes, Doctor.
Great. If you set the TC7 مثلا at value 10,000, so you will count from 0 to 10,000, then reset. 0 to 10,000, you reset. 0 to 10,000, you reset. Okay. So this is what this bit does. At this point of time, maybe we don't need this. To enable the timer overflow flag, we can set the TC the prescaler. The prescaler is how fast the TCNT is going to count. Okay, how fast this is going to be count. It controls the prescaler that would be applied to the bus clock. So we have prescalers from 1 to 128. Multiples 2 to the 0, 2 to the 1, 2 to the 2, and so on. These 3 bits. So we can set these 3 bits to compute, to decide how fast we want to increment. I did an example for you on the next slide. So if you copied the slides earlier, I added this new one. So if we want to generate a 1 millisecond interrupt, we want to this timer overflow to happen every 1 millisecond. And we have a 24 megahertz clock. So our clock speed, let me use this. So our E clock, the bus clock, is 1 divided by 24 million, 24 megahertz. This is the value. Let me store it in memory. Where is memory? No memory here. Oh yeah, memory store. To get 1000 microseconds, يعني 1 millisecond, how many counts do we need? How many counts do we need? Let's compute it. يعني 1000 1 microsecond, sorry, 1 microsecond, 1000
24 دكتور.
1000 microsecond يعني 0.00
01.
لا 1 على طول.
1 على طول.
Yes.
This is 1 millisecond, صح? 1 millisecond.
Yes.
Divided by the thing I stored equals 24,000. So to count for 1 millisecond, you need to count 24,000. طيب 24 counts معناته كم؟ 1 microsecond. So 24 counts will give you 1 microsecond divided by 4.166 period, 24. 24 counts will occur, means 1 microsecond. ILU يعني micro. طيب times 1000 يعني 24,000 counts is 1 millisecond. So if we want to generate an interrupt every 1 millisecond, then we need to make sure our Tcnt counts 24,000 times. طيب, so we know it is 16-bit, صح? 16-bit يعني the maximum value is 65,535, but now we're talking about 36 counts to overflow minus 24,000. So this is the initial value, Tcnt initial value. You write it in your code initially for 41,536 in your main program. You initially write it. Then this is not going to count yet before so this start counts when after we enable the normal operation, after we enable this, after we write TSCR1, صح? So TSCR1 should be wrote afterwards, بصراحة. Okay, so let me fix this code. So TSCR1 before we enable the count. So I'll update the slides after the class. ماشي? Before enable the counting, we need to enable other stuff. Yani we don't want to enable and we don't. And the TSCR2, we enable the overflow interrupt. We enabled the overflow interrupt, but we did not start counting yet. So we did not start counting, so no interrupt will happen. That's why we enable the interrupt. Then we start counting. We write a 90. This is the value we just computed. ماشي. And then enable global interrupts. Enable interrupts. Afterwards, the Tcnt will count from 41,000 to 65,000, yani 24,000 times. It will cause an interrupt. Then your program counter will gonna come here. The first thing you do inside the interrupt, you rewrite the initial value, okay? Because if you don't, it's gonna go back to 0 and count 65,000 times instead of 24,000 times. So you write the initial value again. So it will keep counting 24,000 times every time before coming into the interrupt. And we don't forget to clear the flag before we delete the interrupt. The flag is in the register called tflag2, bit number 7. This is a timer overflow flag. Okay. How do we clear it? By writing a 1 to it. So we write a 1 to it, bits number 7. It's only 1 bit. Others are not used. Okay, and this is CD code. You can write whatever you want here inside. Whatever you write here will be executed every 1 millisecond. طيب, what if I ask you to use Tcnt counter to create a delay function called myDelay, just like when we did in the RTI interrupt, and I pass it milliseconds. Okay, what would you do? you can just do I here plus plus, صح? So you increment I every 1 millisecond. In your delay, you reset I to 0 and keep waiting for it while I is less than the milliseconds you want. Stay stuck here. When you're done, return. So we can write hardware-based delay interrupts here, delays here, using the Tcnt periodic interrupt. Clear يا جماعة؟
دكتور يعني هون
تفضل.
دكتور ليش عملت انه اي بلس بلس؟
يعني if you want I to increment every 1 millisecond, and you use it in a delay function, you keep waiting for it. يعني I'm just giving an example of application. If you want I to increment every 1 millisecond, and then you use it inside a function to where you reset I to 0, and I will count, مثلا you want delay 100 milliseconds. While I is less than 100, stay stuck in this loop. When it reaches 100, you're released. So this delay will cause your program to get stuck here for 100 milliseconds, or 1,000 milliseconds, or whatever. We did an example, I remember, but using real-time interrupt. If you want to enable something every amount of time, yani if you want to blink the LEDs every 500 milliseconds on, 500 milliseconds off, you can increment J, مثلا J++, and say if J equals 500 milliseconds, صح? Turn on LEDs, or port B, if it's on port B or port H, equals the complement of it, port B. Then reset J back to 0. So this will make J keep counting from 0 to 500, 0 to 500. Every time this condition is true, you can go flip the LEDs or do whatever, or enable a task. Tamam? So you can write whatever you want here. You will get into here every 1 millisecond. If you want every 10 millisecond, well, this will not, you need a prescaler maybe. Here the prescaler is 1. طيب, you want half millisecond, 500 microseconds, this is divided by 2, صح? Instead of 24,000, 12,000. So on. This is the idea. Mustafa, did you want to say anything?
لا خلاص كنت بدي احكي عن الديلي اللي هو الملي سكند بس خلاص اوكي.
Is it clear?
Yes.
Okay, so we're done with the free running timer. We're done with the free running timer and we're on time, huh? 6:15. So I'm good. I think next time we can go deeper in input capture. So we're done with the free running timer. It's طيب. If we want to do different time computations, this is prescaler 00. We initialize these to 0. طيب, if you want to create every 2 milliseconds, you can set this to 001. صح? You get a prescaler, then your clock is not 24 anymore. It is what? Divided by 2. صح? The time is multiplied by 2. You're at 12 megahertz now. So the computation, everything changes, صح? So you don't need to count 24 times for 1 microsecond. 12 times would be for 1 microsecond, صح? And 12,000 times would be for 1 millisecond. طيب, if I want 10 millisecond, 12,000 times is not enough. You can go even divide by 2, صح? So you can go change this value, another divide by 2, by 4. By 4. احنا الكلوك تاعتنا كم؟ how fast is it? 24 meg. 24 meg. طيب, another 2. Then you're getting بتصير 1 millisecond every 6000 صح؟ طيب 10 millisecond you make it count to 60,000 times 60,000 بتصير 10 millisecond. But in this case, you need to use a prescaler of 4. So you can play with these numbers to control how fast you're counting, and you can compute how many counts to achieve a certain amount of delay and compute the initial value. Clear يا جماعة؟
Clear دكتور yes.
طيب so we stop here 6:15 6:16. Thank you very much. See you Wednesday. Have a nice break. You can stay. I'm going to stop the recording. You can stay if you have any questions.